Hey there, and welcome to today's Explainer. As a senior data scientist, I am absolutely pumped to step into the mentor role for you today. We're going to dive straight into this explainer and demystify how machines actually learn, breaking down some pretty complex algorithms into a really clear visual journey. So go ahead and forget all those science fiction movie tropes because today we're looking at the real mechanics of our modern world. All right, let's start with a real-world mystery. It's kind of the very first question every single entry-level student asks when they look at modern AI. I mean, we all know machines have dominated factory floors since the Industrial Revolution, right? But recently, they've completely leaped from physical labor to cognitive tasks. They're judging competitions, they're driving our cars, they're even beating grandmasters at chess. So how exactly are they doing all this if a human isn't sitting there meticulously typing out a specific line of code for every single possible decision? Well, before we answer that, we really need to talk about why you are here. 95%. Let that sink in. According to research on the future of automation, 95% is the staggering probability of professions, like chartered accountancy, being fully automated by the year 2035. And it's not just accountants. Waiters, receptionists, taxi drivers, they're all facing similar odds. But here is the silver lining for you. While old jobs fade out, there is this massive, incredibly fast-growing demand for skilled professionals who can actually design and manage these intelligent systems. Industry demand is totally outpacing the supply of data scientists. So your timing, it's literally perfect. To really grasp where we're headed, we actually have to jump back to 1959. This brilliant quote here is from IBM's Arthur Samuel, and it's based on his incredibly famous checkers experiment. He basically wanted to see if a computer could outplay its own creator. And in doing so, he essentially coined and defined the entire field you're about to enter. It was really the first massive indicator of humanity's drive to impart our own natural system of learning right into man-made machines. Okay, keeping to our strict zero jargon policy today, let's clearly define what this means before you even think about writing a single line of Python or C++ code. Machine learning is, quite simply, a subfield of computer science. It gives computers the ability to learn and improve from data, completely without being explicitly programmed for that specific outcome. It's the whole shebang of self-learning, detecting patterns and boosting performance based entirely on empirical information. Now, before you start building your very first model, I've got to let you in on a little secret. You absolutely must understand that classical statistics are the foundational blood and oxygen powering these machines. We're talking layer upon layer of linear regression, random forests, massive equations, honestly, the exact same math you probably studied back in high school. These statistical algorithms surge through the machine and literally drive all of its cognitive abilities. Let's actually compare traditional programming side by side with machine learning to see the massive core shift in thinking you need to make today. In traditional programming, it's pretty straightforward. You give a rigid input command, like typing 2 plus 2 into Python, and boom, the machine gives you a direct action or output of 4. But with machine learning, we don't feed it commands. No, we feed it input data. So, the absolute most crucial takeaway here is that machine learning operates on this very specific 3-step workflow. First, we gather our input data. Next, the machine analyzes that data through a ton of trial and error to decipher patterns, which forms a statistical model. Finally, that shiny new model is used to generate a predicted action or output. Data, model, action. Seriously, make this your new mantra. Okay, let's make this real. Think about a spam filter. If you use traditional programming, you'd probably tell the computer, hey, block any email with the words PayPal and payment. But what happens when an actual, legitimate PayPal autoresponder emails you a receipt? The traditional code totally fails. It triggers a false positive because it relies on static, rigid rules. A machine learning model, though, it adapts. When it makes an error, you can modify its assumptions, teaching it over time that emails from payments@paypal.com are actually totally safe. Think of it kind of like this. It's exactly like training a guide dog. At first, the dog learns from specialized training, right? Experiencing how to heel at a red light or how to carefully walk around a hazard. By recording those experiences over and over, the dog eventually doesn't need the trainer's direct commands anymore. It can apply its learned experience to completely new, unsupervised situations. Well, our statistical models, they do the exact same thing. Now, you might be wondering, how is this different from data mining? Well, imagine 2 teams of archaeologists. The data mining team excavates a site,
finds some treasure, and then moves on to a completely unrelated site the next day. They're just looking at the past. But the machine learning team, they excavate a small pit, study the tiny variances and patterns in the dirt, and then they use that past experience to build a strategic model predicting exactly how to best dig the next pit. Machine learning continuously optimizes the future. All right, let's just take a quick breather for a big picture summary. I want to make absolutely sure you have a rock-solid mental framework before we peek under the hood at the algorithms themselves. Remember, it is built on a foundation of high school statistics. It relies entirely on that three-step workflow of gathering data, building a model, and predicting an action. And it completely thrives on continuous learning rather than static, unbreakable rules.
Okay, let's shift gears and look at the actual mechanics, seeing how this builds into the tools you'll be using on the job. Now, machine learning incorporates hundreds of different algorithms, but as a data scientist, your very first task is choosing the right overarching category. We generally divide the field into three main branches: supervised learning, unsupervised learning, and reinforcement learning.
First up, we've got supervised learning. This branch works entirely with labeled datasets. Basically, that means the correct answers are already completely known to the machine during the training phase. You feed the machine sample data that has various features, and you explicitly tell it what the correct output is. The machine's only job is to decipher the hidden relationship connecting the two. To see this in action, imagine we want to predict the selling price of a used car. Our inputs, what we call our X variables, are attributes like the year it was made, the brand, the mileage, things like that. Now, because we're using historical data of cars that have already been sold, the machine already knows the final price, our Y variable. The algorithm just works backward, finding the mathematical patterns between the attributes and the price to create a rock-solid prediction model for future cars. But listen, as a professional, you can't just trust a model blindly. No way. To guarantee accurate performance, you always have to split your data. First, you use a training set to actually build and tweak your rules. Then you verify the model's accuracy on the remaining data, which we call the test set. Only when it knocks it out of the park on both is it truly ready for the real world. Next up is unsupervised learning, and honestly, this is where things get truly fascinating. Here, the data has zero labels. The machine has absolutely no idea what the correct answer is up front. Instead, the algorithm is forced to uncover hidden structures entirely on its own, hunting for similarities and organically forming its own groupings. Take a super popular unsupervised technique called k-means clustering. Imagine plotting a massive set of customer data based purely on their cloud infrastructure purchases. Without you ever stepping in to label who is who, the algorithm groups those data points around distinct centers all by itself. It naturally separates the mom-and-pop shops buying basic hosting from the massive enterprise customers buying advanced firewalls, purely based on their completely different buying habits. And here is where I see this having a literal game-changing impact in the real world. There's a company called DataVisor that protects networks from cyber fraud. Now, traditional supervised learning really struggles here because hackers are always changing their tactics to dodge known rules, right? But DataVisor uses unsupervised learning. By analyzing millions of accounts and hunting for incredibly subtle, suspicious correlations between users, they can identify entirely new, unclassified sleeper cell attacks before the hackers even strike. They find the fraud without even knowing what the fraud looks like yet. It's wild. Our final and probably most advanced category is reinforcement learning. Unlike the first two we talked about, which eventually reach an indefinite endpoint once a model is formulated, reinforcement learning never really stops. It doesn't use tagged outputs. It just continuously improves through iterative feedback. It tries an action, gets graded with a score, and then uses that score to do better the very next time.
You can visualize this exactly like playing a video game. Actually, picture an algorithm called Q-learning playing Pac-Man. The machine learns by exploring the maze totally randomly at first. Every single time it hits a ghost, its score drops. That's a penalty. But every time it eats a power pill, its score shoots up, a reward. By obsessively recording these positive and negative feedback loops, the algorithm eventually learns the absolute optimal, flawless path through the game. Wow, we have covered a ton of ground today. From the classical high school statistics secretly powering these models right up to the distinct, incredible powers of supervised, unsupervised, and reinforcement learning. So as your mentor, I'm going to leave you with one final challenge. You now grasp the foundational three-step framework of how machines actually learn. You know exactly how to turn data into a model and a model into an action. The demand for your new skills has literally never been higher. So, what intelligent system are you going to build first?